So some of you might know me. My name is Jyoti Matam. I'm based out in Dallas, Plano office. I'm a worldwide system simulation industry process specialist at Dassault Systems. I've been with Dassault for almost 6 years now, working mostly on implementing the simulation workflows within the 3D Experience platform on system simulation topics and so on. So I let Saulius introduce himself.
And the pleasure to work with Jyoti is for me, Saulius Pavalkis. I'm MBSE ecosystem senior manager.
Okay, coming to the agenda, like I said, we are bringing two worlds together, which is systems engineering and system simulation, using the standards, open standards. Let's say we have to emphasize on the open standards, which is SysML and Modelica. So we talk about the advantages, what is the integration, or how exactly we can make the integration between these two from the tools perspective or the language perspective, and then we are going to show you a quick demo about how the integration works and how well you can utilize it. And then, of course, we are going to talk a little bit about the summary and the conclusions about this integration strategy.
So first of all, talking about SysML, it is and system engineering is not isolation. It's not an isolation, and there is no silo here, especially as the role system engineer is the one who connects the dots, right? So, and also we can see here from the beginning, SysML, so system engineering was always in integration with requirements, with the documentation generation, and the most important with the analysis. There are great opportunities to do analysis, but we need to digitally get the data from system architecture to verify requirements or to do trade studies. So as a result, we can get performance characteristics that requirements with that architecture is verified, and that this is the best architecture. And then we also integrate with the design for the model-based design continuity, digital continuity in mechanical, electrical, and Dymola supports two roles here with the multiphysics design. It leverages design for the analysis and also allows to do the performance characteristics, again, multiphysics environment. So one more slide on SysML, because that's what we use for system architecture modeling, and there are multiple views. Why those views are important? Because we start from user needs analysis in order not to miss what actually user wants, first of all, from the system. And there is use cases for that to capture user needs and scenarios, how they are supported. As a result of that, we come up with system requirements for the system, which we satisfy with solution architecture, alternative solution architectures in block diagram, in internal block diagram, and then also behavior side of that, because systems could be stateful, right? How they react on the events and what they do can depend on the state, especially the electrical software systems, right? So state, machine, and functions as activities allocated to the structure, especially if we talk about the software intense systems, right? So there's definitely logic and functions in software, which is allocates again to the hardware. So that's like the main parts of the SysML, and as you can see here, a lot of analysis are needed to come up with optimal solution architecture to clarify requirements, and for that we can leverage multiphysics simulations coming from Dymola, and Dymola can leverage system architecture coming from SysML.
Yeah, that's precisely correct. Okay, so now let's look at one of the examples from the system simulation point of view. Here we have an aircraft model thanks to Dassault Aviation, Thomas from Dassault Aviation. So here we have 5 subsystems. As you can see, electrical systems, cabin, braking, and so on. As a part of the subsystem, we have like about 10 test cases per each system and thousands of mission data per study. And when we look a little bit deeply, the entire system model consists of like about 200,000 equations. And at the end, we have to also think that we have to also look from the perspective that this has to be validated against the requirements, functional analysis, and you have to also validate with the organization, meaning there are different people working on from the different departments, so there has to be a synchronization, right? So this is precisely what we want to address with this integration of systems engineering and system simulation, to have that continuity between the interfaces from one silos to the another silos.
So talking about that integration point, so as initial step, let's talk about MBSE maturity model from the simulation perspective. This model actually comes from Lockheed Martin Senior System Engineering Manager Chris Schreiber, Lockheed Martin Space Systems. Here we see at the first step, we have those ad hoc models. When we have independent models coming from SysML as a separate requirements modeled coming from Excel, coming from like some Visio diagrams, let's say Modelica or MATLAB, right? But they are not glued together, right? So everyone has those models for many years, right? That's like nothing new, right? Then we have system architecture in single place, right? That says SysML, right? We captured already system architecture, and that's nothing more than system requirements, system architecture requirements, like functions, parts, interfaces, what we need to have. It's not what we have to do analysis, but what we need to have as a final system. So that's what we have, and then we can execute. Why we execute? First of all, to validate the logic, executing SysML. Some people say why you would simulate SysML, but it's not about simulation as this kind of multiphysics or something like that. It's actually just to validate the logic. And then next step is to run in the context of the analysis which are performed by the dedicated analysis tools like Dymola for multiphysics analysis, in order to verify those requirements to do actual analysis based on system architecture. That's the fourth maturity level of MBSE adoption. So if you already see someone is already modeling system architecture in SysML, they already know SysML simulation. We can actually integrate now and we can run that full scenario. And also another step is that actually next we can optimize and come up with the optimal solution, especially if you introduce new products, if you introduce changes to existing products, if you have variation in your products, all of that can be maintained. We don't need to redo the model, we just change the parameters to introduce new use cases and optimize again on the solution architecture. So now that also leads us to the value of this integration, right? So first of all, the different purpose, right? When we talk about multiphysics simulation, we talk about simulation of the system model which already exists, right? So we have the system model, we can optimize, we can actually come up with the trade study of the system model, but when we talk about user needs analysis and transition to solution architecture, optimal solution architecture, that's ability to have in SysML. So we have this Dymola model, SysML model working together to come up with the optimal solution architecture and to verify requirements based on the actual multiphysics environment. As a result of that, we have Dymola high fidelity multiphysics models and libraries available for early stage low fidelity system architecture analysis in SysML. Also, we have consistency between the models. So you can imagine that variants of system analysis and system architecture will be generated. Variants of new iterations, new products will be modeled, so we need to know which versions of the models are integrated, and enterprise architecture management solutions like 3D Experience Platform allows to track the not only life cycle of the models, but also which versions and who produced them, and that traceability still holds.
Okay. Coming to the workflow itself, we start off here the integration, from the integration perspective, how exactly the workflow would look like, and this is kind of a proposal. It would start off with importing of Modelica connectors. As some of you already know that we have, since Dymola is a multiphysical simulation tool, it's equation based, acausal and so on. We also have an existing libraries that come with Dymola. So for example, Modelica standard library is one of the standard library which consists of interfaces for all the physical aspects, that disciplines that you can think of, right? So the idea is we import those physical connectors into the SysML, and based on that you have your definition of your system architecture, your test cases, scenarios, models, everything pretty much based on the requirements, different states from the different stakeholders perspective embedded in the Cameo. And then from the second step, you have your interfaces, you have your systems architecture, you kind of create template model out of this from the SysML to the Modelica. So here's the transition that happens from step 2 to step 3, where we are actually translating the SysML elements into the Modelica elements, which consists of kind of an template model with all the interfaces, with all the parameter sets that are coming from the requirements level. So from the point 4 or the step 4 to the step 5, what we are doing is, like in step 4, we are kind of utilizing the benefit coming out of our the SOL libraries. It could be a commercial libraries or open standard libraries, as we are talking about open standards like Modelica. So you can also bring libraries coming from the outside based on the Modelica language, and you can extend your system architecture and embed the actual physical behaviors to it in step 4. And then you execute your models, you validate your system. Of course, this is not going to be a one step. There's going to be an iteration between from 4 to 5 in order to find the right optimization of your system model. And then at the end, what we could do is, like from the simulations, we could validate the simulations results against the requirements that were initially defined, and which was also based on your system architecture was also based on your requirements, right? So precisely we are connecting the dots, starting from defining your architecture up until your validation. And additional benefit that we can have here is like taking the value of Catia Magic, where you can have multiple variants of your system, and you can do the simulations on the kind of a trade analysis or design of experiments could be set up, and you can actually find an efficient system and have an early phase of validation, I would say, with this kind of a workflow. About the system simulation portfolio itself, as I mentioned, if you remember in the previous step, we were talking about extending the system architecture based on the libraries coming from the outside, from commercial libraries or open libraries, right? So within DSO, we have got multiple libraries based on different industries. It could be for the powertrain, for the thermal systems, for your mechatronic systems engineering, for controls, everything. So there's a lot of data or data sets available based on the industry, and you can just plug and play based on the use cases, I would say.
And those libraries are the key value because they give immediately the physics behind them, right?
Yeah.
So you then can count on them and leverage in your product. So this is like as getting system reference architecture when you model in SysML like satellite. Okay, there's like typical satellite. Okay, we can update now the model instead of creating everything from scratch.
Yeah, exactly. You can just take the benefit of the existing models. Okay, and then we have one of the examples that we are going to show today with our video is about the battery electric vehicle. To be precise, most on the charging of your battery. So the use case is in such a way that we want to understand, or based on the requirement, the charging of your vehicle has been changed from, for example, 40 minutes to 20 minutes. So this was kind of a requirement that you get, for example, from a stakeholder, and you decide to build up your system model. So when we look or take from the perspective of the previous workflow, we start off with importing of the Modelica connectors into your Catia Magic, and then you build up your system architecture based on the use case. So here I'm talking about electric vehicle as a whole, but here one of the sub use case that I'm interested in is the charging behavior, right? So for that particular use case, I have my system definition here, and if you look a little bit closely, the internal block diagrams from the Catia Magic and the block definition in Modelica, of course, look the same. I'm talking from the interface perspective, not from the physical point of view right now. So this is the benefit that we want to take to have the synchronization between Catia Magic and Dymola here. So here we are translating the a subsystem or the system from the Catia Magic into step 3, which is my charging behavior. Typically, when you want to do the simulation for charging behavior, you have like a charger, you have your battery, you have your cable models, you have your thermal management system, and some auxiliaries. So this is the definition overall that you can think of, and this has been again enhanced further with the existing libraries, physical models coming from Dymola. For example, we are using battery library, we are using thermal management system library, and we are using electrified powertrains library, and so on. So we kind of use the existing content or the data sets and plug and play here. So once you enhance or enrich your system architecture with your physical models or behavior models, we are finally verifying and validating it against the requirements which were set up before. And one good thing here we are going to show you also is the trait analysis. So let's assume that I have a different battery models, meaning like, you know, I have a battery A and battery B. The battery B has a better thermal performance compared to the battery B. Battery A, how exactly am I going to, you know, compare it against the requirements? So such kind of a trait analysis could be easily done, and again you're doing it like a continuous flow, so there is always a continuity, and whenever there is a change in, for example, in the architecture, your system model will be updated, so which will actually save the time. And you know, starting with the first example, so let's start off how exactly the synchronization looks like. So just a quick glimpse of about the workflow itself. Let's start with the first part of the conversion. So I actually have to talk a little bit about this conversion. So we've been talking about converting the SysML elements into the Modelica elements, right? So how exactly is this happening in Catia Magic? So there is something called as SYSPHY specification that you should be aware of. So SYSPHY stands for System Extension for Physical Modeling. So what that it is almost it is like similar to how we have got open standards like FMI and so on. So SysPhys is actually coming from OMG organization, and the specification, if you look back, it actually gives you all the information of how you can connect parameters, requirement parameters defined in Catia Magic or in SysML language into a Modelica parameter, how exactly a block can be converted into a Modelica block. So such information is part of the SysPhy specification, and this is exactly what we have done, and this implementation is being done in Catia Magic for all of us, starting from, I don't know, from 21x or 20x, I assume. And you can take the benefit of directly just exporting the models. So from the step 1 to 4 is the SysPhy specification that we are going to talk about. So if you look into a little bit about the magic grid of your electric vehicle here, so I've got some information on the requirements, for example, for the charging time in this case, and the entire vehicle architecture itself. But of course, for my use case, the interesting part is the battery pack and the charger model, very few sub blocks, but still we have the entire system structure definition here, along with the requirement parameters and so on. And the use case, as I mentioned, the sub use case out of this architecture is my charging model or the behavior model. And that's exactly what we are doing here. And if you look into the interfaces, again, you have to remember that the interfaces could be imported directly from the standard libraries, as I mentioned. So in our case, Modelica standard library, as you can see in this containment tree, it consists of interfaces for all the disciplines, like for the electrical, for the fluid, for the magnetic, for mechanics, and so on. So for me, the interesting part was for the battery, and for the battery, it's obviously electrical. So we assign the ports directly coming from the Modelica standard library here in this case. So you will understand the difference, or you would understand the meaning once we go into the Dymola world, let's just say that. So here, once you apply your codes and everything, so here I have the block structure or the internal block diagram with all the interfaces and everything defined between each of the components. And now what I could do is like quickly translate it into a Modelica model. So this is exactly what we are doing here. So at this level,
could I add one more thing?
Of course, please.
Yeah, I know it's this architecture we interchange, but it's not necessarily complete architecture, because you might have some things which makes no need for the analysis, right? And you want to be sure that you have captured everything, what is important, right? For that battery analysis, and then that's what we transfer to like some this aviation, for example, call it architecture for the test case, right? But I'm not sure that this is a good completely term, but it's not bad term, right? Because we are testing and we are performing analysis in some context, right? So we are delivering. So that's actually also gives us like freedom for us not to say, okay, now we need to transfer everything from one language like SysML to another language like Modelica, which is like impossible because those are different languages, right? So there is some overlap, and that's what we want to translate based on the need of the analysis. Am I right?
Yeah, absolutely. So that's exactly what we are doing today.
Yes.
We are taking the sub use case out of the entire architecture, precisely.
Yeah, subset of that.
Yeah. Okay, so here I wanted to say that we have like a couple of options again when you're exporting your SysML model into a Modelica model. Of course, we have the definition. To some of you who can understand the Modelica language, we have the definition of a different, we have parameters, we have variables. There is a difference when we look from the simulation point of view, right? So that difference, of course, you can still apply from the SysML side. As you can see, you have got those options, whether your definition of your parameters is actually a parameter, or it's a variable, or it's a constant value. This actually makes a big difference, right? So, and along with that, you can have the definition of your annotations, meaning the location of your system, and so the location of your components, for example. So when I bring this model directly into the Dymola, you can see that the interfaces have been respected. What I mean by that is to most of you who understand the Dymola tool, you can actually see that the positive pin and the negative pin are actually the physical entities have been defined, and the definition has been respected. So this is what this is the benefit that we wanted to take through the connectors, like importing of the connectors precisely into the Catia Magic earlier and get them. And the text layer looks similar, and if we go a little bit back, I guess I missed the part where I wanted to show you the parameters, for example. So we have some list of parameters as well, and then at the end we have the flexibility to change your models, meaning add behaviors on top of it. So I could add the battery behavior, I could add the charger behavior, and similarly I did for the rest of the system, and this is how the entire system would look like. This is very fast.
That's okay. So you kind of redefine those components with the existing models.
Yeah.
Could be library, could be already existing in the company context.
Yeah,
right?
yeah, exactly. And you might think that, okay, I see some extra additional components, so I just added some auxiliaries which were actually not part of my system definition, but I did extend my system here, and this is how the entire system model would look like at the end. Okay. Coming to the second part, which I wanted to discuss, is about the validation, right? So now we have the first part was like kind of bringing or merging the SysML into Modelica together. That's good, but we have to take the somehow it has to be useful, right? So we need some useful results out of it. We want to validate the system against the requirements. So the V&V is something that is also precisely important. So for this part, what we do is like there are multiple ways to do this. This is not the only way. Let me put it that way. So first is you can convert or you can generate an FMU out of the system model that we just created and integrate it into Catia Magic and make the simulations and compare them against the requirements. That's one way to do it. And the second approach that is possible is a direct Dymola integration. So here again we are talking about standalone tools. Maybe this question might come rise in your head. So we are still talking about standalone, not the 3D experience platform. So the Dymola integration, what it means by that is in Catia Magic you have the flexibility to bring directly the Modelica files, the MO files, and simulate them within the Catia Magic itself, and that is possible through the Dymola integration. What happens in the background is So you can execute the simulations of Dymola either with the tool, or we have the flexibility to do it with the functions, with the scripting functions. We call it as scripting functions or command line functions. So we typically use it for batch simulations. So that's precisely what is being used here in this process. So what we do is like we directly take the system model that has been generated in the previous step and execute them through the command line scripting functions from the Catia Magic. So some of the functions that you should be aware of is called as like simulate extend model or multi extend model. What this means is like you can pretty much use this function, which is a command scripting function of Dymola, from the SysML, and you can execute your Modelica files. And of course, this integration is being supported both on Linux and Mac operating systems, so it's flexible. And I have not tested it for the team workload projects.
It will work.
I'm assuming it should work.
Yeah, it works. It doesn't matter.
Yeah. And yeah, so the second part of the validation, this is what I was talking about. So we have you have generated your system model, and you have done a couple of iterations, and you have to find the right optimized system model, right? So we are going to do the verification and validation part against the requirements now. Let's quickly look into the example or the continuation of the previous model. So here, this is what I was talking about. There are a couple of integrations possible, third-party integrations within Catia Magic. One of them is, of course, Dymola. And here, once you integrate it in the background, what happens is like the instance of your Dymola is being executed every time you run your simulations. So that's exactly what is done. So here I have a very simple activity diagram, as you can see, and what I'm doing is like there are a couple of informations that I'm providing, because I'm setting up a trait analysis here, which we are going to see, and in the background this activity diagram is being simulated. So here what I've done is I wanted to, like I said, I have the system model ready. I wanted to check for the two different variants of the batteries. So I wanted to take one battery which has a better thermal performance, and wanted to see for a different configurations of the battery whether my requirements are satisfied or not. And all the different physical aspects, like the temperatures, the losses across the cables and everything, which are also equally important. So I wanted to make a validation of all of that. So that's exactly what we are doing with this instance table that has been created. So in the background we are simulating this activity diagram, which in turn consists of the Modelica model itself, which is executing the simulate extend model of Dymola, and it is sending out all the input parameters, which is like the change in the configuration that I tried to simulate, meaning I wanted to simulate it for different configurations, like I said, for the number of cells in series and parallel. So we are varying these parameters. This information is fed from the Catia Magic into my Modelica model, and in the background you are actually running your behavior model. We are not talking about any static simulations here, we are actually talking about the physical simulations. And at the end of the simulations, you can see the information of, for example, for me the interesting information on the variables were the weight of the battery and the charging time. So this is exactly for example, the battery prismatic A2 is aligning to my requirements, but the rest of the the rest of the configurations do not. And we have some configurations of the battery prismatic, which is the type B is also aligning to my requirements for both the charging time and the battery weight. And we have, of course, a couple of other informations about the currents, temperatures, losses, and so on. But this is to give you a glimpse of how better you can take the benefit of bringing SysML and Modelica together, and how you can validate them. You can complete the loop and validate them against the requirements which were defined initially.
Yeah, so we are bridging the gap, and I would say it's not like really gap, it's actually those languages, they are very popular. We dedicated Modelica for multiphysics simulation, SysML for system architecture, and transition from user needs to optimal system architecture, and delivering as the optimal architecture for the design with the help of the simulation, as you saw. So we are connecting that in the best ways. Those integration steps are the best we have with any other tools, And now, because we are now part of the same company, we can actually work together on that, and also for proof of concepts work together. And those things, again, ability to leverage system engineering process from user needs to system architecture in optimal way, integrating multiphysics models for ability to do trade studies, for ability to do verification based on those analytical models, gives us edge on this in this world. It's kind of competitive, when we talk about system simulations in general, right? But we have best of the class solutions, right? So, and also another thing, that we have consistency between the models. Even those tools are standalone, but you can put the models in the configuration management and the 3D experience platform. Then they have the version, they have the workflow, and we have the owner, and we can see the connection between them as ability to track who produced what version, and then are those versions integrated based on the content, and this is the benefit. Again, we have the best integration between SysML and Modelica from all the analysis tools and all the system modeling tools. Pretty much SysML and Catia Magic pretty much is the leading here. So we have the great story and great expertise, great team working together.